Welcome back to AI Paper Podcasts.
Yeah.
If you look at the big AI revolution, the last few years, especially with LLMs, the real story is unification. They cracked it, right? Found this shared language transformers plus simple tokenization, like BPE. Suddenly one model handles reasoning, code, translation pretty seamlessly.
Yeah, it just works, but try applying that same idea to computer vision. You hit a wall, a big one.
Totally. It's just fragmented. Deeply structurally fragmented.
Exactly. Language. It's discrete, symbolic, easy, relatively speaking, to tokenize. Visual data, though, it's continuous, it's messy, it lives in totally different worlds.
Right. You've got specialized systems just for 2D images, then completely separate models, often for video, dealing with time.
And then there's this whole other universe for 3D. Meshes, voxels, splats, all needing different approaches for, say, reconstruction versus understanding.
So the fundamental problem, really, is that no single tokenizer has managed to bridge all three images, video, 3D, and be good at both generating pixels and understanding the semantics. Until maybe now.
Well, that's the claim. That's the mountain researchers at Apple decided to climb.
And that's what we're diving into today. The paper, AToken, a unified tokenizer for vision. They're proposing this single, universal visual language across images, videos, and 3D assets.
Yeah, it's ambitious. So our mission today is basically to unpack how AToken pulls this off. We'll get into the architecture. It's this novel, pure transformer thing operating in 4D space.
And that adversarial-free training method, that sounds really interesting.
Oh yeah, it's key. Plus, we'll look at the results, which seem to suggest that this could actually be a foundational building block for, well, all of vision AI. Start of 1-minute key insight summary.
Okay, so for those needing the quick technical summary right now, let's hit the key insights from the AToken paper.
All right, Insight 1, unification. AToken is really the first visual tokenizer that manages strong semantic understanding and high-fidelity reconstruction. And it does this across images, videos, and 3D. Plus, critically, it supports both continuous and discrete tokens downstream.
Insight 2, the architecture. It's a pure transformer, no convolutions in the tokenizer itself, and it operates in this sparse, unified 4D latent space-think feature coordinate pairs. The dimensions are time, X, Y, and Z depths.
And the magic ingredient making that 4D space work?
Ah, yes. 4D rotary position embeddings, or 4D ROPE, that's what lets it handle different resolutions and video lengths natively.
Okay, Insight 3, stability. Transformer tokenizers often struggle with Jan training instability. AToken sidesteps this completely. They ditched adversarial training for a stable, adversarial-free objective.
Ow.
It combines perceptual loss with this novel Gram matrix loss. They found that targets feature covariance texture style, which apparently accounts for like 86% of reconstruction errors. Pretty clever.
Okay, and Insight 4, performance. Does it actually work? The benchmarks look good. A 0.21 RFID for image reconstruction quality, that's really solid. 3.01 RFVD for video fidelity. And for 3D understanding, 90.9% classification accuracy. It looks like a genuinely universal foundation. End of 1-minute key insight summary.
So stepping back a bit, why is visual tokenization so much harder than language? We touched on it, but language being symbolic, discrete, that lets things like BPE just map everything to simple tokens. Knowledge transfers easily.
Yeah, visual data just isn't like that. It's continuous, high-dimensional.
And that difficulty really shows up in two main ways in visual AI. First, task specialization.
Right. If you, as the engineer, want amazing image generation, like really fine details, you probably reach for a VAE or a convolutional model. Think SDVAE or VQGN. But those are often not great at understanding the meaning.
Exactly. Pixel accuracy over semantics. Then conversely, you have models built purely for understanding like CLIP or SIGLIP2, amazing at high-level features, linking vision and text.
But they often can't reconstruct the original image worth a darn. They throw away that low-level detail. So you've always had this trade-off, fidelity or semantics. Doing both well, that's been the challenge.
And the second split, modality fragmentation. Images are 2D grids, video adds time, 3D. Well, that's a whole mess of different representations.
Wow.
Meshes, voxels, NeurFs, Gaussian splats. And most models pick one, maybe two. Video models might handle 2D, sure, but they usually ignore 3D entirely. And 3D models, like Trellis Lat, they're stuck in their geometric world.
Which brings us to the architecture problem. Transformers are awesome for scaling understanding tasks, we know that, but using them for high-fidelity reconstruction tokenizers, the ones needing adversarial training, historically very unstable. Mode collapse nightmares.
Okay, so AToken aims to fix all of that. Let's unpack their core idea, this unified 4D space.
Right. Instead of dense grids for each modality, everything image, video, 3D becomes these sparse 4D feature coordinate pairs. So you have a feature vector, $C's and dollars, and its position P to P.
And that position pairs is literally 2 LSE, X, Y, Z, Xi, EZ, time space coordinates.
Precisely. So a single framework handles everything. An image just sits on the XY plane, time T0, depth C, ZL is 0.
Makes sense. Video.
Video just extends along the time axis. Phi de vary, ZL says 0. It's a natural extension.
Okay, but 3D. That seems like the trickiest part to unify. How do they represent complex 3D assets in the same TLSE XYZ0 space? They represent them as surface voxels. So T0 is 0, but 6xt dollars now define points in 3D space. The clever bit is how they get those features into the voxel space.
Ah, okay. They don't use a separate 3D encoder.
No, that's the key. They adapt a technique kind of like Trellis Sell-It. They render the 3D object from multiple viewpoints.
Okay.
Apply their standard patch embedding process to those 2D views, and then aggregate those 2D patch features back into the 3D voxel grid based on camera position and geometry.
Ah, very clever. So the same patch processing works for images, video frames, and the views of 3D objects. That's real unification.
Exactly. And the architecture enabling this is a pure transformer. They start with a pre-trained vision tower, like SIGLIP2, but generalize it.
Using those space-time patch embeddings in the 4D Ropey you mentioned.
Right. The 4D rotary position embeddings are crucial. Ropey is good at handling variable sequence lengths, so extending it to 4D lets AToken deal with different image sizes, video durations, and 3D voxel grids without needing retraining for every new size. It interpolates.
So once you have these unified 4D features encoded, what happens then? You said it handles both reconstruction and understanding.
Correct. The system projects those features in two ways. For reconstruction or generation, they're projected to a lower dimension, $0. This can be a continuous latent space.
Good for smooth generation, diffusion models maybe?
Or it can be quantized using FSQ, that's finite scalar quantization, a simple, fast method to get discrete tokens, like for an autoregressive model.
Okay, so that covers the generation reconstruction side. What about understanding?
For understanding, they take those same encoded features as Zeroveller and use attention pooling to create a single global representation, let's call it Darlar.
And that's the bit you align with text embeddings for classification, or VQA.
Exactly, that's the semantic vector. The crucial thing is using the same base features for both generating detailed pixels and capturing high-level meaning. That's the unified part.
Okay, now let's get into that stability issue. You said this is where previous transformer tokenizers really fell down. They tried JANs for the high-fidelity output.
And it just blew up. They mentioned in the paper that in their pure transformer setup, the discriminator got way too strong, way too fast, led to immediate mode collapse. The generator just couldn't keep up.
So their solution wasn't to fix the JAN, it was to get rid of it entirely.
Very much. They went adversarial-free. But first, they did this really smart diagnostic analysis. They looked at the reconstruction error using the RFID metric.
And they found?
They found that something like 86.6%, huge chunk of the quality loss wasn't about getting the basic shapes wrong. It was about the covariance component, texture, style, high-frequency stuff.
Wow, 86.6%. So the problem wasn't the main structure. It was the fine detail, the texture matching.
Precisely. The mean features were mostly okay. The covariance was where it failed, and that insight directly led them to the gram matrix loss, or little gram.
Because gram matrices capture style and texture information, right? They measure feature correlations.
Exactly. So by adding a loss term that directly optimizes this feature covariance, they could get that high-fidelity reconstruction, the sharp textures, without needing an unstable discriminator. It's a really neat piece of engineering.
So for images, the full loss function has several parts.
Yep. For images, it's L-Delta1 for basic pixel matching, LPS for perceptual similarity, making sure it looks right to humans, their novel levelgram for texture, and LPA to keep it semantically consistent with the text model's understanding.
That's quite comprehensive, but they simplify for video and 3D.
They do. For video and 3D, they found just using the L-Delta1 loss was enough. They rely on the power of the image training and cross-modal transfer to get the details right in those modalities. The image foundation is doing the heavy lifting for texture.
Okay, fitting all this together, images, video, 3D, reconstruction, understanding, sounds complex. How do they train it? Just throw all the data in at once?
No, that probably wouldn't work. They used a careful 4-stage progressive training curriculum. Makes sense.
Stage 1.
Image foundation. Basically, take the pre-trained SIGLIP2 base and add the reconstruction head, get that working well on just images.
Okay. Stage 2.
Video dynamics. Now they bring in video data, expand the latent dimension a bit from 32 to 48, and add optimizations like KV caching to handle the longer sequences efficiently.
Stage 3, the big one.
3D geometry. Now they add the 3D voxel assets, represented at 64 cubed resolution. And interestingly, they also increase the image resolution training at this stage.
And stage 4.
That's optional but important. Discrete tokenization. This is where they add the FSQ quantization layer to get those discrete visual tokens if needed for downstream models.
Okay, that progressive approach makes sense. But here's something really surprising you mentioned earlier. Multimodal training actually helped the single modalities.
Yeah, this was pretty cool. They measured image reconstruction quality, RFID, after stage 1 image only, and got 0.258. But after stage 3, after adding video and 3D training,
It got better.
it got significantly better, dropped to 0.209 RFID. That's a 19% improvement in image quality just by learning about video in 3D.
Whoa, so forcing the model to understand time and geometry actually made it create better representations for static 2D images. That implies the different modalities are teaching each other and forcing a more robust internal representation.
That seems to be the implication. But there's a catch. This synergy, this cross-modal benefit, it requires capacity.
Ah, the scaling analysis. What did that show?
They trained a smaller base model, about 192 million parameters. When they tried to add video and 3D to that model,
Didn't work so well.
it got hammered. Image RFID degraded by nearly 50%. It went from okay on images alone to terrible when trying to juggle all three.
So the smaller model just couldn't handle the complexity. The features started interfering.
Seems like it. It proves that you need a certain model capacity for this kind of ambitious unification to actually work. The larger Ceph 400-meter model they used thrived. The smaller one failed. Size matters here.
Okay, so assuming you have the capacity, let's look at the final validation. The benchmark results. Does AToken actually deliver as a unified solution?
The numbers look pretty convincing across the board, yeah? Both for fidelity, how good the reconstruction is, and for understanding.
Let's hit fidelity first. Images.
That 0.21 RFID we mentioned, significantly better than previous unified attempts like Unitalk.
Video.
The continuous token version got 3.01 RFVD. That's getting close to specialized CNN models designed just for video reconstruction, which is impressive for a unified transformer.
And 3D reconstruction.
They reported 28.28 PSNR, which measures the accuracy against the ground truth geometry. That actually beat the specialized trellis SLAT baseline it was compared against. So yeah, the 40 thing seems to capture geometry well.
Okay, that covers fidelity. What about understanding? Classification retrieval?
Also strong. On ImageNet zero-shot classification, 82.2%. For video, text-to-video retrieval accuracy was 40.2% R1, and for 3D, that 90.9% classification accuracy on ModelNet 40 is very solid.
And critically, does this improved tokenizer actually help downstream models, like multimodal LLMs?
That seems to be a key validation. They plugged AToken into an MLLM architecture, slow-fast LV 1.5, replacing its standard vision encoder.
Yeah.
Performance went up, consistently improved across various scales on standard image reasoning and VQA benchmarks like RWQA and SCALA, compared to the Oryx VIT baseline.
So AToken isn't just good in isolation. It provides genuinely better visual features for these big multimodal models.
Yeah.
That's strong evidence for its generalization.
Right. And briefly on generation, it's competitive there too, 1.56 GFID for continuous image generation. But maybe the bigger deal is that it enables discrete token generation across all three modalities effectively for the first time in a unified way. The qualitative results also look good, better detail, sharper text images, better color on 3D models thanks to that gram loss.
Okay, let's wrap this up. What's the big picture takeaway here? AToken seems to have genuinely cracked the visual fragmentation problem.
It really looks like it. They've successfully mapped images, videos, and 3D into one shared visual language. That's something people have been chasing for a long time.
Built on a robust transformer, that clever 4D representation, and critically, that stable adversarial-free training using the gram loss.
Yeah, those are the core technical pieces. It provides this unified, stable foundation. The paper itself gestures towards this, enabling the ultimate omni-model.
An omni-model. One model to handle everything visual.
One set of visual tokens that could potentially feed a single universal generative model capable of operating across images, video, and 3D space and time.
Which leads us to the final provocative thought for you, our listeners, especially the researchers out there.
Yeah. Yeah.
Given AToken's unified tokens, what's the next really complex cross-modal task this could unlock?
If you can truly encode detailed 3D geometry and how it changes over time into one consistent token space, could we finally generate, say, a complex dynamic 3D scene directly from just a text prompt?
Synthesizing a whole movie, essentially,
Right.
but in interactive 3D?
Maybe. That kind of unified generative omni-model that feels like the frontier AToken has just opened up, something for you to explore.